Honey, don't walk out, I'm too drunk to follow. You know you won't feel this way tomorrow. Well, I'm a little rough around the edges and inside a little hollow. And I'm faced with something sometimes that are so hard to swallow. Hey, but I was born a rebel down in Bewley on a Tuesday morning. Of 1 foot in the grave, 1 foot's on the pedal. I was born a rebel. I was born a rebel. She picked me up in the morning. She paid all my tickets and screamed in the car and let me out of the ticket. I never would dream that I was so wicked. I keep coming back, cause it's so hard to kick it. Hey, hey, hey. I was born a rebel down in Big Sam on a Sunday morning. 1 foot in the grave, 1 foot tall. Girl, I was born a rebel. I was born a rebel. Even before my father's father was called it so rebel. They burn out our crops and they levels our town. I still feel the eye of those red coated devils, and I'm walking around tonight through the concrete and metal. Hey, hey, hey. 'Cause I was born a rebel. Up in Bewley on a Tuesday morning. I'm 1 foot in the grave, I'm 1 foot on the pedal. I was born a rebel. I was born a rebel. Hey, hey, hey. I was born a rebel. I was born a rebel. I was born a rebel.
Hello, everybody. So you asked me for a long time to play one of these guitars, so I did. And I joined the other rebel. And okay, let's start with today's little chat here. Hope you can hear me well because I've got a slightly different setup today. Alex knows if still everything okay. Okay, sound? Yeah. Good. So the first thing I have to say, like I always say, short disclaimer, whatever I'm saying today that is not necessarily shared by CERN. I am called the man from CERN here because I worked at CERN for all my life, but I quit 11 years ago, retired. And so now I am an independent scientist. So what you hear from me is certainly my own views. And well, for the second thing, I tried to improve the network connection because last time we lost the network a few times. This time I did a little bit of work by passing cables outside the balcony so we could connect directly into the hub. But if I go away for some time, don't worry, it's just a couple of minutes and then I'm back. I live in an island in the middle of the ocean, and therefore this is expectable. Now, I'm going to pass on the presentation as usual. So let me, I think we already have it, yes? Alex, you have the presentation?
Yeah.
So let's go. And let's start with a little introduction. I've done some research because there have been a few questions about CERN being built on top of an Apollyon temple. Apollyon being some sort of bad Roman god. So I did some research about this. And this is what I found. This is the Large Hadron Collider that you see drawn over the area of Geneva. Geneva is this part near the lake. Oh, can you see my mouse? Yes, you can. Good. So is this part near the lake. And this yellow line is the French-Swiss border. As you can see, the Large Hadron Collider sits mostly in France. CERN actually, as the lab is here. Here's a little city, a little campus of CERN down below where it says Atlas. Below there, there's CERN. And Atlas, LHCb, CMS, and ALICE are the 4 big experiments on the Large Hadron Collider who are looking for the Higgs boson, for antimatter, for dark matter, whatever else they can find. Just anything will go. So, as you see, the Large Hadron Collider is mostly in France. So I believe, I read over the several conspiracy sites, and it looks like this idea of LHC being built over this Apollyon temple stems from the fact that this village here is called Saint-Genis-Pouilly. Now, somehow this Pouilly was related to Apollyon. Somehow it sounds like it. So they think, oh, Pouilly must have been called that way because of some Apollyon. So I checked it out, and in fact, Apollyon, called also Apollon or Apollo in Etruscan, was a Greek and Roman god, but he was a god of prophecy, music, poetry, archery, and medicine. So he was a good god, right? Not some kind of doomsday guy. So instead, another angel called Apollyon appears in the Bible. Now, in the Bible, this Apollyon is the angel of death, destruction, and the netherworld. So, well, you can see that, of course, there were no angels or demons in the Roman religion. Plus, of course, you didn't build temples to angels or demons. The Romans built their temples to their gods, and Apollyon was not one of them. He was a god, an angel that came obviously much later than the Roman and Greek. And another thing to be said is that, there were no temples that were ever found or built here. Why would you build a temple in the middle of nowhere? I mean, that place, there was no settlements in that area. That area was pure forest. There was absolutely nothing. And Romans didn't build temples in the middle of the forest. They built temples in their settlements. And in fact, the nearest Roman settlement there is Nyon, which is 30 kilometers to the east of Geneva, of this area. So there was absolutely nothing in that place. However, one thing that was found in Saint-Genis-Pouilly, or near, actually it was the other side of the Large Hadron Collider, but according to the etymology of the term of Saint-Genis-Pouilly, the historians find that the name Pouilly comes from Pauliacum, which is Latin from Paulus' house. And when we dug, well, it's a CMS up there. Well, when we dug that pit for CMS, we did find foundations of a Roman villa. And it is believed to belong to Lucius Aemilius Paulus. So here you go. Saint-Genis-Pouilly was actually named most likely from this consul. It was a Roman consul that eventually built a villa there, as they did when they retired, like we do. I've retired, I've come to Mauritius. This guy's retired, and he went to live up there near Geneva to play in the casinos. Well, which didn't exist yet, but... So, however, I also found another very, very scary thing. In the middle of the Large Hadron Collider, right there, well, there is a village called Ornay. This Ornay is in the middle of France. And guess what we found there? A Burger King. Can you believe it? A Burger King. That is an offense to French cuisine. So be very, very scared, terrorized of the ghost Whopper. And talking of ghoulies, I take you through another little research I did. The famous Gotthard opening, right? With the devils and whatever, it's Lucifer or whatever you think that is. Well, I actually went and checked the choreographer with the choreographers that put this play together, this dance together. I still have my contacts down there in Switzerland and in the Swiss dancing. So this was inspired at this thing. You know what this is? Well, it's a traditional mask. Like in Africa, they do this dancing with these wooden masks. Well, guess what? In the Gotthard, or rather all the Swiss Alps, there is a moment during the year when the cows go up on the mountain, springtime, and they take the cows up on the mountain when the snow melts to eat the fresh new grass. And the shepherd make this sort of processions wearing these clothes, exactly like the one worn by the people there in the dance group. So you'll see masks like this, which are not meant at all to be ghoulies and devils. These are just wooden masks in the Swiss tradition. In this, in Swiss German, they all look like that. It's a sort of Halloween for them, taking the cows. Look at this guy, how scary he is, But it's just a costume, a cultural, local costume. And you will find so many of them. This guy is dressed as a Yeti. and if you meet this guy, I bet you're scared up there on the mountains, right? But these are actually good things. He's actually up there on the mountains with his cows wearing this mask. So you can actually go there and buy your own mask in the shop. There's a shop of masks, so you can come back and dance like the Gotthard people if you wish to. Now, why were they naked or nearly naked? Well, this as well is part of the culture in Switzerland. You know that Switzerland is probably the only place in the world where you can go hiking in the nude. Why would you do that? Well, it's a law. You can actually do that. And that's because being naked, according to the naturalist, it's a way to connect better with nature. So they go hiking. Well, I don't mind hiking nude. I just wouldn't like to do it without shoes because I'm sure it must hurt on the stones. So that's a way to connect with nature. So that's what it is, the whole story. It's just an expression of Swiss costume and culture. So welcome to Switzerland. And on that note, let's move on to more serious things. So today we will tackle the hard bone of relativity. And that's where really things don't start not making sense anymore by us pure terrestrians. Let's start with, sorry, I have to go back one slide. I clicked too fast. Here, I just want to quickly recap what we said, because some of you may not have seen the previous episodes where I spoke about the Big Bang and dark matter and antimatter. So I'll just go very, very briefly over this. The Big Bang was a huge explosion of pure energy that materialized out of nothing and created our universe 13.7 billion years ago. Within the very few fractions of a second, the universe inflated tremendously to a huge size. And as it inflated, it cooled down. So it was started very, very, very hot. We're talking about trillions of degrees Celsius or Fahrenheit, doesn't matter, it's still trillions. And then it started cooling down. And as it cooled down, this pure energy crystallized into quarks and electrons, protons, nucleons. And it took like 100 seconds after the Big Bang, the first nuclei started forming, the nucleus of the atom, of course. And then it took 380,000 years before we can start seeing the formation of atoms. And we even have a picture at this moment that some special radio telescope could take. They took the remnants of the radiation of this period, of the Big Bang at this period, which allowed us to kind of evaluate how much matter and energy there was in the universe at that time. Much later came, atoms, then came stars. First gases, then gases start clumping together by gravity and became stars. Then it took like 12 million years for that. Finally, 2 billion years later, we could start having the first solar system, the first galaxies, and eventually life, like on Earth, possibly elsewhere. So that's a little bit of a timetable of the Big Bang. But what you see out there, all the things that you can see, the galaxies, the stars, the 2 trillion galaxies, and many trillion stars and planets eventually, is nothing but 4.7, less than 5% of the primordial universe that we caught in that famous picture called the cosmic microwave background radiation. So we are missing most of it. What was produced in the Big Bang by the big flash, Now we find so much less. We find only 5% of that. And the rest, because we cannot see where it is or what it is, we can see where it is. We cannot see it. We can detect it. We can guess where it is, but we cannot see it. So it's invisible. That's why it's called dark matter. And the same for dark energy, which is 68% of what was in the beginning. So how do we know that this dark matter is there? Well, because the rotation of galaxy doesn't make sense. Our galaxies rotate in a way that is like they were stuck on some kind of gel, not in deep space. And this doesn't, add up to our calculation and does not correspond to their mass. There must be some extra mass there that we cannot see, much, much bigger than the mass of the galaxy. That makes it rotate in that way. We also saw last time, 2 months ago, how gravitational lensing gives away the place of this dark matter. Gravitational lensing, as we will see later on in Einstein's relativity, is a phenomenon by which, if there is a huge massive object there, light can be deflected. So light does not move in a straight line anymore, as it would if there was nothing. If there is something there, then light is deflected. Therefore, stars appear to be in places where we know that they are not. Again, we will see this later in more detail. So we don't know what dark matter is, and this is the mystery of dark matter. We need to be able to track it, possibly in our Large Hadron Collider, in one of the experiments, so we can study it. If we can catch it, even for a split second, because if a whatever it is particle that forms dark matter appears in our particle accelerator, in the Large Hadron Collider, it will disintegrate in less than a picosecond, a billionth of a second. So we have to be extremely fast in going and find out, its parameters to try and work out what it is. Then we spoke about antimatter. Now, we know what matter is. Matter is on the left here, you have a lithium atom, just an atom, Could be hydrogen, could be carbon, whatever. We chose a lithium there. And like any atom, it's got electrons turning around a nucleus. In the case of lithium, we have 3 electrons and 3 neutrons, plus, 3 protons, plus 4 neutrons. The electrons, as we have studied at school, have a negative charge. The protons have a positive charge. It's like a battery, plus and the minus sign. Well, the same thing. These things, particles are charged like that. And this is in a way what creates electricity after all. So the electrons in a normal atom of matter are negative and the protons are positive. Antimatter is exactly the opposite, the mirror image. Mirror as long as electric signs are concerned. So we see that an anti-lithium atom, that's whatever you call lithium becomes anti-lithium. Hydrogen is anti-hydrogen, etc. Anti-lithium has positive electrons and negative protons. The positive electrons, we call them positrons, and the negative protons, we call them antiprotons. In the same way, we have quarks and antiquarks. We have photons and antiphotons. All particles basically have their anti-equivalent, which is a mirror image. Even the neutron, which does not have an electric charge, has an antineutron. Well, the reason is that whenever you create these particles, or rather, when we create them at CERN by smashing protons together or by smashing a particle beam into a polarized shield, into a material, a very thin material, or during the Big Bang, or inside the sun, all the time, there is this transformation of matter into energy and energy back into matter. So if we flash electrons or gamma rays into some material, we will then split some particle in that material and dematerialize it for a split second. It will become a flash of energy, gamma rays. From these gamma rays will come out an electron and a positron, one negative, one positive. You cannot create just an electron. You have to always have a symmetric partner. The same thing for protons, etc., etc. So on the other end, when you take an electron and a proton and they meet, when they meet, they annihilate in an explosion of pure energy. We are talking here of microscopic, invisible, not even feel. You can't even feel these explosions and flash of energies. This happens at the level of particles, which is way, way, way beyond what a microscope can see. So electron-positron gives total annihilation and ends up in gamma rays. So this is the phenomenon called annihilation. So at the beginning of the universe, in the early universe, there was a massive matter-antimatter annihilation. Why? Because from this flash of energy, when, remember, started crystallizing within a few milliseconds, then the first electrons were created, but also the positrons. So you can't create an electron without creating the positron. So when this came to become, matter, because electron has a mass, is although very small, or protons, you have to create protons and antiprotons at the same time. It's like you could always have twin babies, one boy, one girl. There's no way to have only one boy or only one girl. That's the law in quantum physics, in the particle world. So when there was this huge matter-antimatter annihilation, this particle were created, but also annihilated because they met each other. We were in a very early universe, like a big bubble, and they kept going all over the place. So an antiproton created would sooner or later meet a proton and annihilate in a flash. This means that all the created matter would disappear instantly back into radiation, and we would not exist. So why are we here? And here we go. This is the second mystery that we are trying to explore at CERN. Why do we exist? if you can't generate only matter, you also have to generate the antimatter, and matter and antimatter disappear in a flash. Now, we come now to relativity, which is the universal law that governs the universe. And in 1905, a gentleman called Albert Einstein came up with this equation that absolutely everybody, every baby knows at the age of 3 months old, E equals mc squared. What does that tell you? Well, it tells you that energy and the mass are two sides of the same thing. They are equivalent. There is an equal sign. Means energy equals mass times the speed of light, which is a constant. So if you take a certain mass, you multiply by the speed of light square, 300,000 square, go work that out, that's a huge number, then you will have how much energy you obtain at the moment of the disintegration of that mass. And another thing that this tells you is that the speed of light is a constant, which is not quite 300,000, just a little bit less, 299.999, it's like in the supermarket. It's never 300, it's always 299.999, So that's the speed of light, and it's a constant, and it's the maximum speed there is. You cannot, or anything cannot go faster than the speed of light, and that's a very known fact. Another thing that comes out of here is that space and time are not two separate things, but they are two sides, again, of the same thing, or rather they are the same thing. They are a continuum that spreads around the whole universe. The whole universe is a space-time continuum in 4 dimensions. 3 of space and 1 of time. Now, 11 years later, Einstein came with another great idea, because he wasn't happy of being such a clever man. He said, let's try to make it even more complicated so that the students really have to burn the brains, to understand relativity. And he created the general relativity. Now, try not to learn the formula by heart. This is much harder than the previous before. But what I put it there because look only at that G on the left side. That's for gravity. And on the right side, there is time, T. Plus, under there is the famous speed of light, c, which is this time to the power 4. Now, this means that although they're not equals, they are related. Gravity and time are related. And as a matter of fact, gravity itself is a curvature of space-time, which is created by massive objects. So an object that sits in space-time will create a well, a gravity well, like a ball, you will see it in a minute, that is proportional to the object's mass. And the second thing that we can see there is that mass and radiations are affected by this curvature. So once it curves space-time, other masses of other things that passes in the universe, asteroids, planets, satellites, they are affected, they curve by following this well created by some bigger massive object. An example is the sun and the earth. There it is, the picture I wanted. You see, the earth is sitting in the little well. Imagine space-time is that grid, that white grid. The earth sits in space-time and creates this sort of well. Now, what happens is that the moon, which is much smaller than the earth, it also creates its own well, but it's a tiny little well. And the moon will be orbiting around the sun, around the earth, like this, by following the inner sides of this well. And in fact, it's spiraling in there because it's falling onto the earth. This little animation shows you, for instance, the earth and the sun. As you can see, the earth is now turning around the sun and it's on the edge of that well. Now, imagine a beam of light was coming through. It would be deflected too. Light too, right, will take the shortest line, which is not the straight line. At the time of Isaac Newton, you see, there was they didn't understand what it was. Newton called this the fact that the moon was around attached to the Earth, was turning around the Earth, as a mysterious action at a distance. But gravity comes really from the interaction of space and matter. Space, I would say rather space-time and matter. John Wheeler said, space-time tells matter how to move. Matter tells space-time how to curve. So that massive objects would always curve space-time. And this is why planets are orbiting around the sun, even though they're extremely far away, because the sun is so big that it creates such a big well that is as big as the whole solar system. And so the planets are trapped into the edge of this well, just like a marble in a sink, in a round sink. Imagine put a marble, it will turn around before it falls to the bottom. The same thing. This is really what happens in 3D, because so far we've been seeing simplifications just for you to visualize it. But in real, space-time is 3-dimensional, and actually it's 4-dimensional. So that's what really happens. Now, this Eddington in 19, I can't remember, 30 something. Was 19, I think. Yes, during a solar eclipse, he managed to prove the light bends around the sun. In fact, this star that will be seen where it says actual location was instead seen farther away because the light beam was curved by the sun. Same way, light, we said, moves, is a constant, and is a constant for whichever observer. So that if you are standing with a flashlight projecting light, and somebody is on a train, let me just stop it for a second, it goes too fast. Somebody was on a train moving at 2,000 miles a second. Well, they haven't, even the bullet trains are well below that, 2,000 miles a second, which means, yeah, speed of light. Somebody was moving at the speed of light. Well, this guy, the light projected by him, will still move at the same speed. Whereas normally, if you are on a car and you throw a ball, now imagine you standing there and you throw a ball. Say the ball goes at the speed of about 2 meters per second. That's if you launch a basketball, anything, a ball, you launch it. So what happens is if you launch, now the ball will in absolute move at about, say, 2 meters per second. However, if you are on top of a car that is already moving, say, at 10 kilometers per second, then you launch the ball forward and the ball will go at 2 meters per second plus the 10 kilometers per second of your car. Well, for light, it's not that way. Wherever you launch the light, whether it's on the train or standing on the ground, the light will always move at the same speed of 300,000 kilometers a second. It can't go faster because that's the speed limit of our universe. So now back to gravity. We see, for instance, that if we send 2 light beams, one going near the Earth and one going in deep space, of course they are traveling at the same speed because there's only one speed. However, the light beam that passes near Earth will be subjected to gravitational field where the other will not. So we'll have to do a longer path, the one above, than the one below. This means that because the distance is different, but the speed is the same, there's nothing we can do but understand that something, distance or time, must change. Because otherwise that equation would not, sorry, what happened to my presentation? Disappeared. Okay, come back. Here. All right, well, I was at the end of this animation. Sorry, it went too fast again. Let me go back to this picture. Right. So either time or distance or space must change. So what happens really is that when you go very fast And if you could, we cannot go any faster at all, but we cannot even think of nearing the speed of light. Like I said, 300,000 kilometers a second, right? That's the distance between the Earth and the Moon in 1 second, roughly. So we cannot do that. We cannot take a spaceship and go to the Moon in 1 second. But what happens is, if we could, say, go to a speed near that, say we could do half that speed, well, the time would expand and the distance would shrink. It's something that is mind-blowing. So how can the distance shrink? If I'm going from New York to Los Angeles, well, that's always the same distance, no matter how fast I go. Not true. If you were to go at a speed near the speed of light, then the space you are actually covering is much less, and nearly zero if you can go to the speed of light. It's crazy, I know. And nobody can really understand it unless you really go into the maths. And even if you do go into the maths, say, yes, okay, this 2 + 2 = 4, but I still don't get it. So, however, this is true because, from a perspective of an astronaut, people who are in the ISS, we have put a clock on the ISS, and the clocks run faster than the clock on Earth. These were two identical quartz clocks. And if you swap them, that's the same thing. So it's nothing wrong with the clock. The same way, GPS, when you are navigating with your GPS, we have to take into account that the speed of light, because we have to adjust for the GPS to go to the satellite and back, to communicate with the satellite. Because if the guy has to track you, he has to take into account the speed of light and the fact that it's not in the same reference system than you, which is Earth. We know he's out there, and because he's out there, he's not subject to gravity. We saw that light is curved by gravity. So he's not subject to gravity, which means that for him, time passes slower than us. So if you were to go into space and spend there a year, you will come back a few seconds younger, depending how long you spend there. But if you spend, that's the famous twins paradox. There is two twins. One of them goes into space, the other stays on Earth. And the guy spends 10 years in space, 10 years of Earth. But when he comes back, he's only a month younger, a month older than he left. And that is because he was going very, very fast, say close to the speed of light, whenever we will invent those kind of spaceships. So your GPS, you're using relativity every day when you navigate with your GPS. Think that you are using Einstein's equations. So we were saying that gravity is a curvature of space-time that is proportional to an object's mass. So the bigger the object, the bigger this well into space-time. So on the left, you can see that's the well made by the sun on top left. Then below, there is a white dwarf, which is a sun that has collapsed into something, a dwarf star, really not very big at all, but very massive. And then a neutron star, which is even more massive. This is when the star has used all its fuel, has burned all its nuclear fuel, and now is left only with neutrons. And these neutron stars are, of course, extremely massive because neutron is a massive particle, which doesn't burn. So it's a star which is off. It's not producing any light. But it makes an even bigger dip into space-time. And finally, on the right, you have a black hole. A black hole is something that is so massive that the well it creates is, in theory, probably infinite. Now, let's talk a little bit about black holes, because I know that a lot of you want to know about them. And they're called the scavengers of the universe. And why? Because they keep wandering around the universe unseen, because we cannot see them with our telescopes. We can just imagine that they are there because we see some strange effects, as we will see soon. And they are basically some, they call black because they absorb light. They absorb light, they absorb everything that falls in it, planets, stars, entire galaxies, and light. Light doesn't come out of it, no radiation. So we cannot tell where they are, because the only way you can tell what something is if it reflects light or it generates light. There must be all light or radiation, can be gamma rays, can be X-rays, anything it could generate will tell our eyes, our telescopes, or our radio telescopes that something is there. A black hole is really a black hole. Everything ends in that, and that's it, disappears. So gravity in a black hole is so high that it prevents anything to escape. They're normally formed by the gravitational collapse of dying stars. So these are star corpses. They are dead or dying stars. Because what happens is, well, sometimes supernovas can end up in that way. Imagine a supernova that explodes. And supernova can explode and become 20, 30, 100 times bigger than it was at the end of its lifetime. We're talking about stars, big stars, not the sun, huge stars. What happens is that at the same time that it explodes, it also implodes. And why? Because the whole volume of that bowl of gas explodes at the same time. So it will explode both in this direction and in this direction. And the part that explodes inside could actually implode into something extremely heavy and concentrated mass that could eventually become a black hole. So it's either the collapse of dying stars or supernova implosions. They have to be minimum 3 solar masses. Okay, and this is when, okay, I'll come back in a second. But a black hole, to become a black hole, a star, must be at least 3 times our sun. That means our sun will never become a black hole because it's too little. And this connects to the question that keeps coming about CERN making black holes. The micro black holes, not even visible with a microscope, don't last even 1 billionth of a second if we never even saw them, because if we do create them, then they disappear before we can even track them, because they, like all the other particles that are creating in the LHC, they immediately vaporize and revert back in normal particles, in protons, in neutrons, and they decay into the particles we know, the electrons, the photons, the things that we see in the everyday world. So these strange things like micro black hole are only transitional elements, particles, that are formed in the collisions, proton-proton collisions, or they're formed in the sun, or they're formed by anything that squashes matter into energy. And they survive only 1 billionth of a second before disappearing. A real black hole, to be a black hole, one of these things that goes around the universe and eats stuff, has to be at least 3 times our sun. So, well, they believe, I'm talking about mathematical scientists, about mathematicians, theoretical physicists, that they could actually reach a space-time curvature that could be even infinite. So imagine a hole in this thing, this tunnel, this sort of well that goes down becomes like a tunnel, like a cylinder, and it disappears down in the abyss of space-time, should I say. We can see something coming out at the poles. That's why this particular picture, you see some jets coming out top and bottom. These are jets of radiation, which is normally gamma rays or X-rays, and they actually come from the accretion ring, which is basically the moment when the stars, the planets falling in there, are disintegrating. The gravity is so big that you get sucked in, you get slandered, you get completely disintegrate into your atoms when you fall in there. And therefore, you become pure energy. Any mass that goes in there, from a rock to a sun, will become pure energy, pure radiation. And this is called the Hawking's radiation, because he's the guy who found what it was. Now, can they be shortcuts through space-time? Well, some people believe yes, others no. Well, in any case, that the theory could probably admit that this could become portals to connect through a wormhole to another black hole somewhere else in the universe, or somewhere in another universe. There are several theories. We all have seen the story of the paper that you fold in two, space-time, and you have, I'll do this again, I did it the other day, but you have here two black holes. I don't know if you can see my black holes. They're not very black. Well, all right. There's two black holes here and there. And now, because these black holes make a well in space-time, they make it so big that these two wells can actually, they could bend space-time so much that two holes can actually be connected one to the other. So if you go through one black hole, you can come out from the other. That's the idea of wormholes. We will see this in a video in a minute, how this could happen. Now, what we call point of singularity means a point where the energy is infinite and times zero, this sort of things that in mathematics, when you end up in hitting infinites, you end up with the most impossible explanations. The gravity is so extreme and it bends, space-time, as we said. They could act, here is my little paper exercise where two black holes in two different parts of the universe could actually connect to each other and make a wormhole by bending, warping space-time. Now, according to Einstein and Rosen, they would connect to the same universe, just a different part of a universe. According to Schwarzschild and others, they would bring you to a different universe. And now we're going to talk about, we will talk in another day about the multiverses, the different universes, and whether that can exist. But in any case, it's unidirectional, and you would not be able to cross because you go through it, but then you get trapped in the middle. And why? Because in the middle is where the black holes are, and they are the thing that suck everything in. You see what I mean? So the wormhole is not possible you couldn't possibly traverse it because you would get stuck when you find the black hole. It's like a magnet. Magnet is in the middle and it catches you. So, that's the end of the slides, but I would like to show you a little video now. So I'll change my presentation to a video. Okay, this is a video that you probably heard about Michio Kaku. He's a very good communicator, science communicator. He's a very good theoretical scientist. But, I chose this video because it's actually very well done, and I hope you understand it. All right. So let me start from the beginning. No, quite QuickTime Player is a bit slow, my computer today. Okay, let me try again. There he is. Okay, here's it. This is Michio Kaku.
We physicists have waited 100 years since 1916 for this photograph.
It is a region black holes might just be one of the most fascinating and mysterious phenomena in the universe. They are massive beasts in terms of power, but at the same time, virtually invisible to us.
And a black hole weighing perhaps 2 to 4 million times the mass of the sun.
But because of the research that was put into them over the last couple of decades, we've gone from knowing absolutely nothing about them to getting to learn more and more, up close and personal. And things have just gotten crazier. Michio Kaku just announced that we've finally gotten a look at what's inside a black hole, and this new information brings light to the details the world of science might have missed all along. Join us as we dig deeper into black holes and unveil what's inside space's big bad. Before we get into the details of what Michio Kaku found, we have to talk about the firsts. Even though most of us have some idea what black holes are, there are still some gaps in the right information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept of black holes was purely theoretical. It took another 50 years for the scientific community to find evidence that black holes actually exist. This happened in the 1960s. They were studying the Cygnus constellation when they noticed an oddly bright blue star that was emitting X-rays. This star wasn't a stagnant object, but was going around a giant black something. Upon further investigation, it was found that the X-rays weren't just moving around on their own, but they were being sucked into the black thing they were orbiting. Thus, the name black hole. This discovery was significant because it provided proof that black holes actually exist and that we're just a figment of Albert Einstein's wild imagination. While that was great, it also meant that there was this unreal entity in space that we urgently needed to know more about. So researchers all around the world got to work. This black hole was named Cygnus X1, and it is located in the constellation Cygnus, about 6,000 light years from Earth, and it was no small discovery. It's about 14 times brighter than the sun and incredibly dense, which causes it to have a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. This is why it is called a black hole. The concept of a black hole is both fascinating and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, never to be seen again. But that aspect of danger makes it even more necessary to learn everything there is to know about them. Was this it? Or were we just beginning? The answer ended up being the latter. After the discovery of Cygnus X1, scientists started to search for other black holes. They found that there may be close to over 100 million black holes in the Milky Way alone, but because they are so incredibly hard to detect, we still don't have an exact number. Nevertheless, from the looks of it, there are several million black holes in the Milky Way, in our very galaxy, which is what makes them even more important to study. So let's break it down. The main concern with black holes is always going to be gravity. Their gravitational pull is so intense that anything that enters it compresses down astronomically until it becomes a singularity. In simpler terms, black holes are like cosmic vacuum cleaners that suck everything in. One of the scariest parts about the research that's gone into black holes is the fact that if someone were to fall into one, they would get stretched to the point that they become a single line. This process would happen slowly, and the person would die before the final form actually sets in. So let's just say that no one should be stepping into one. But they're all over, so could we really be in danger? Despite the fact that the closest black hole to Earth is 1,500 light years away, it's still close enough to bring up questions and concerns. In 2021, scientists were able to release the first clear photograph of a black hole, specifically the M87 black hole. This black hole was photographed several nights in a row, and with each photograph, the researchers gathered more and more evidence about it. They had to stitch the individual photos together to create something that filled all the gaps. This way, they were able to figure out that there are 3 layers to a black hole. It's not just one single gaping hole of nothingness, as many people believe. Things are a lot more complicated than that. To even get to the nothingness part of a black hole, you have to make it through the first 2 layers. The first layer is called the event horizon, which, while in the first layer, it's the point of no return. Once you pass the event horizon, there's no turning back, and you will be sucked into the black hole. It only gets worse from there on out. The second layer is the photon sphere, which is the region where light orbits the black hole. Any light that enters this region will be trapped and will not be able to escape the black hole's gravitational pull. Finally, we come to the third layer, which is the singularity. This is where everything that enters the black hole gets compressed down astronomically until it becomes a singularity. The singularity is a point in space-time where the laws of physics as we know them break down, and we just can't predict what happens next. At the singularity, the density is infinite, and the laws of physics as we know them cease to exist. Now, what makes all of this infinitely worse is the fact that every single black hole you study will be entirely different from the last. Sure, they do tend to follow the same three-layer concept, but the way they function could be vastly different. Now, if this were anything else, all we'd need to do is hop back on those telescopes and just study the problem at hand in detail. But with black holes, you can't really do that. Scientists can only study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe like the Voyager inside a black hole is not possible because anything that enters the event horizon is pulled towards the singularity, where it is compressed to an infinitely small point. So you can't exactly waste billions of dollars just to get a glimpse every time, because the second the probe gets close enough, it'll just crush into nothingness. Because of that glaring problem, scientists are left with no option but to study these objects in a two-dimensional way, even though they are three-dimensional phenomena in reality. To make matters even more challenging, there are also the two problems of every black hole being unique, and the laws of physics as we know them breaking down when we try to explore the inside. This means that the traditional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean that the researchers haven't been busy. There are lots of different theories and explanations of black holes. And well, with each one, things get more and more interesting. One of the most compelling theories about the formation of black holes is that they are created from collapsed stars. When a star exhausts all of its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward. As a result, the star begins to collapse in on itself, becoming smaller and denser as it does so. If the star is massive enough, this process can continue until it becomes a singularity. To understand the nature of black holes in depth, NASA scientists turned their attention to the core of the galaxy, M87. Astronomers observed a super-powerful whirlpool of super-hot hydrogen gas that was spinning at an astonishing rate of 1.2 million miles per hour. The sheer force of this spinning disk of gas should have caused it to violently fly apart in all directions, but it didn't. Scientists deduced that there had to be a colossal mass concentrated at the center of the galaxy to prevent this from happening. This massive object weighed as much as 2 to 3 billion suns and could only be a black hole. But that's not the only theory where black holes spin. In 1963, the New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a spinning black hole. Kerr showed that a spinning black hole wouldn't collapse into a point, as previously thought, but to a ring of fire or a thin disk. The disk would be spinning so rapidly that centrifugal forces would keep it from collapsing. This spinning disk of matter is called the ergosphere, and it is the region surrounding the black hole where the laws of physics start to break down. But the most intriguing feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical passage through space-time that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a black hole, instead of being crushed to oblivion, one would be sucked down a tunnel through the ring of fire and shot out a white hole in a parallel universe. To understand how this works, we need to look at the concept of space-time. In Einstein's theory, space and time are not separate entities but are interconnected, forming a four-dimensional fabric called space-time. Objects with mass warp this fabric, creating a gravitational field that causes other objects to move towards them. Now imagine a sheet of paper representing space-time. If you place 2 points on the paper and draw a line between them, this is a representation of how objects move through space-time. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole. It's a shortcut through space-time that connects two distant points in an instant. Wormholes aren't just a sci-fi concept. They are actually a prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse almost immediately. But the existence of an Einstein-Rosen bridge would mean that black holes are not just cosmic vacuum cleaners, but could also be portals to other regions of space-time, So, could we use a wormhole to travel through space and time? Unfortunately, the answer is probably no. Not yet, anyway. Even if we could stabilize a wormhole, it's unlikely that we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute limit on how fast anything can travel through space-time. But even then, the theory of wormholes and black holes as pathways to other parts of the universe or even to different times has been a subject of fascination and speculation among physicists for decades. The idea that there might be shortcuts through the fabric of space-time, allowing travel through great distances or even into the past, could possibly be revolutionary if we could actually achieve it. One of the most intriguing concepts in this area of study is the Kerr wormhole, which is named after the mathematician Roy Kerr, who first described it using Einstein's equations of gravity. This type of wormhole is essentially a hypothetical tunnel through space-time that could connect two distant points, such as two different universes or even two different times within the same universe. The Kerr wormhole is often visualized as a ring-shaped portal, similar to the looking glass in the story of Alice in Wonderland. Walking through the looking glass transported Alice to a world where animals spoke in riddles, and logic didn't always apply. In the same way, passing through the Kerr ring could potentially transport a traveler to another universe or another time, where the laws of physics might be very different from those we are familiar with. But at the destination, that could just be normal. While the idea of wormholes as a means of interstellar travel or time travel is certainly exciting, as we've glossed over before, it's also a subject of controversy and debate among physicists. Some have pointed out that wormholes, and particularly Kerr wormholes, might be unstable or impossible to traverse due to the intense radiation and subatomic forces surrounding their entrance. The critics argue that Einstein's equations of gravity, which are used to describe wormholes and black holes, only work for gravity and not the quantum forces that govern radiation and subatomic particles. In order to truly understand the nature of these phenomena, a new theory is needed that can unite the laws of gravity with the quantum theory of radiation. Throughout the world of science, this is called a theory of everything, a single theory that can unite both Einstein's theory of gravity and the quantum theory.
And the theory of everything will be the subject for perhaps a possible, probably the next presentation. So at this time, I would like to call for questions. Alex, if you don't know if you've selected any.
I've got a few. If you've got any more questions, put them into the chat at this time. If you can put them in capitals, it makes it a lot easier for me to pick them out. Okay, the ones I've got so far is this question. I'm coming in late, by the way. I saw a video about time crystals they discovered at MIT. They found a form of matter that could replicate, implying it's intelligent.
Oh, that's interesting. I didn't know that. Time crystals, you call them?
That's what they've said, yeah.
I'll look into it.
Okay, no worries. I think this was going on the graphics to the wells when you had the Earth and then you had the black hole, you had the different types of stars. It said this would apply this an up and down in space. Now, I don't know if that's the case or whether it's just a simplified illustration.
Oh, yeah, because, of course, you are only seeing, we are used to gravity, I mean, to things falling down. So when you stretch a sheet or, and you put a heavy ball in it, that will make that sort of well. In 3 dimensions, you have to imagine that that is in 3 dimensions. So, in fact, that stretching happens in all the possible dimensions. So it's like a sphere. It's not just a well on a flat plane. And in one of the presentation, there was a slide where he actually was showing, one of the clips before was showing a sort of elastomer, a sort of a ball moving through elastic lines. That is probably closer to the representation of gravity wells.
Okay. If the North Star is in the sky is always there, are we following the North Star as we fly through space?
Well, stars don't move much between each other, at least in your lifetime. You can hardly experience the star moving by any dimension at all compared to Earth. Of course, Earth rotates, and Earth also turns around the sun. So rotates around the sun and revolutes, so Earth is constantly moving. Therefore, you see the stars passing by the sky. However, when you are always in the same situation, that means the same day of the year, and the same day of the year and the same hour, so you are facing in the same place, you will not notice much of a difference in the place of that star, of each star in the universe, because you will notice it in terms of hundreds or thousands of years, not certainly in your lifetime. Therefore, in our lifetime, the North Star is in that position compared to the sun, and it will stay so probably for the next 20 generations before they can actually eventually not be in the north anymore, but slightly off.
Okay. What if the black holes are the cleanup crew in the universe, or a portal? Maybe if we knew how to reverse the effects using antimatter, travel possibly?
Any black hole, basically what you saw in this video, black holes could be, one of the theorists, the Einstein-Rosen, wants them to be portals. Things that definitely two black holes could join and bend space-time and join into a wormhole and become portals. Now, as for antimatter does not exist in our universe, if not for a split second every time there is disintegration of matter into energy. So in the sun, atoms are constantly fusing, so disintegrating and becoming pure radiation. So the mass of the protons, the neutrons, the electrons in those atoms of the gases in the sun transforms into pure energy that we feel on Earth as heat and UV rays, and we tan with it, and we feel hot, and we heat ourselves with. But at the same time, a part of the energy retransforms into matter and antimatter. But the antimatter is not long-lived, because it will annihilate instantly against the first atoms that it meets of other particles that it meets in the sun itself. I don't know if that answered the question, but basically, antimatter in our universe is like the unlucky child, is the one that always gets to disappear, because our universe is made of matter.
Mm. And I don't always know how they're thinking, so I don't know whether you're answering it to what unless they put up a subsequent question. But what would happen if we sent an anti-gravity ball into a black hole? An anti-gravity ball made of titanium with eyeball camera built inside it.
Well, that is a very interesting idea for a science fiction film. To bust the black hole by sending anti-gravity to the gravity mass. But yeah, the fact is anti-gravity, it doesn't exist, or rather we have not discovered it. And if it is possible to create it and stabilize it, keep it stable so that we could actually use it as it's in the science fiction films, well, then anything is possible. Now, whether you have enough antimatter, don't forget that these black holes are masses in the order of many times the sun, which means thousands or millions of times the mass of the Earth. So where are we going to find so much anti-gravity to throw in there?
Mm-hmm. That's all the questions I've got at the moment. If anybody else has got any.
Okay.
Unless you would like to weigh in on the discussion that's been going on about whether the Earth is really round or whether it's flat.
You know what? I was thinking today, maybe, I've been running a series of talk here in Mauritius, in Rotary and other clubs, about the science of conspiracy theories. This means I take a conspiracy theory and I analyze it from the scientific point of view. Mm-hmm. And then I let you judge. I don't say it is true, it is not true. But the flat Earth is one of them that I have actually tackled, as well as the moon landing and everything, and analyze it by the scientific method. That means by looking at facts and then deciding, or rather letting the audience decide whether this is true or not. It's something that I could do in the future, but I'd like to finish this set of physics, and basically what we're going to do next is, well, we just saw the theory of everything and the superstrings that lead to it. And this is all a connected theory. That means the superstrings connect to multiple dimensions and to parallel universes. And then, the theory of everything itself is based actually on the superstring and supersymmetry. And I cannot go too deep in it, of course, because it's all very, very deep mathematics, but I will try to find videos like this one, for instance, that can make it more understandable, at least that you can appreciate the idea about it.
Yeah, I'll just have one more pop up. Is there a limit to how many chemical elements, isotopes that humanity can discover?
Well, I guess there isn't. The whole of the uranium isotopes is actually a pretty new family of elements, and they're basically very close together. Atoms that vary in atomic number. So basically, in the number of protons, neutrons, and electrons, and therefore each one has its own characteristics, such as the amount of radiation they can emit and the what they call the half-life. That means the time by which they are still able to emit radiation. I'm not an expert in the field. This is material science, not really physics. It is physics, I guess. But again, it's not my field. So I think that absolutely there may be more, certainly. And we must never think that we've discovered the whole thing, because every time we open a new door, we find there's a whole new garden out there, of weird beasts that we still have to discover. So saying, we know everything about this, or we found them all, it's always wrong, unless the mathematics tells you so. For instance, in the Standard Model, we have been discovering particles. We have been hypothesizing that a certain particle exists, and this will come from a mathematical equation. You do your calculation, say, there must be this particle, but then we haven't seen it. But then maybe 50 years later, we build the instruments that is able to find that particle. One example we saw just before, the theory of relativity. Einstein hypothesized this in 1905, and the special relativity, where he was working on light and the speed of light. And then he did in 1916, he came up with gravity, with the general relativity. But it took 4 years for somebody to actually look at the effect of a solar eclipse and see, because solar eclipse, why? Because that's when the moon goes in front of the sun, and it becomes night, and you can see the stars at the back. When you look at the sun, you can never see the stars that are behind it. But in fact, what happens is that the stars that are behind it, the light that comes to you actually bends, because passes very close to the sun, falls into its gravity well, and bends. So you see, like, the star is not where it's supposed to be, but you see it's, shifted. There is a position shift between the apparent and the actual location of the star. And this was found only 4 years after Einstein hypothesized it. So the same way, particles, we have found a certain number of them, 100 and more, called the particle zoo, which were zoo, like, in animals, particle zoo. And this particle zoo actually corresponds to what the theory of the Standard Model being a theory that classifies particles, in a certain way by families. And all the particles were found. The last one that we had not found was the Higgs. But there are still more. For instance, the famous graviton, we know that gravity now propagates in waves. We just learned that from an experiment, very recent experiment that could record gravity waves coming from rotating, twin supernovas. They were emitting these waves by rotating the ripple space-time like a stone in the water. It makes ripples, and this arrived to us. So basically, or was it a supernova explosion? Anyway, this events in our galaxy or other galaxy, supernova explosion, galaxy merges. When two galaxies hit each other, that happens. Galaxies actually merge. I mean, they go in head-to-head collision. 100 million stars with probably 1 trillion stars, and they go into collision. Imagine what that is. So, but that creates ripples in space-time that can propagate gravity waves. So we've recorded gravity waves on Earth, and we therefore must imagine that there may be a particle called a graviton. So we haven't seen it, but because it's very difficult to track. But maybe one day we'll have the technology to do it. The same applies to materials, to elements, etc.
Aren't the stars that we're seeing, sorry, it moved up just as I started reading it, that we see in the sky actually dead?
Oh, good question. Some of them maybe, because when we say a star is, for instance, 5 million light years away. We can see stars that are 5 million light years away. Even billions of light years. We recently saw the farthest light, which was, I believe, 12 billion light. So one of the very first stars that formed near the Big Bang time. It was like 10 or 12 billion years, light years away. Now, certainly that star that we just saw doesn't exist anymore, because a star cannot live 12 billion years. So the light came to us. But what we were seeing was the image of how that was when that light left 12 billion light years ago, 12 billion years ago. The same way, when you look at the sun is 8 light minutes, correct me if I'm wrong, I think it's about 8 light minutes away from us. So when you look at the sun, well, if you could look at the sun without getting blind, the light that reaches us, the heat that you feel on you, left the sun 8 minutes ago. So you are actually you're looking into the past. The same way, when you look at a star like Andromeda, which is, I can't remember, a few light years away, Proxima Centauri is the closest star to us, and it's only a few light years away. And but this means that when you see that star, you're looking at how it looked back then, when the light left there. And now you cannot know. It's like, once upon a time we used pigeons, right? And we put the message on the pigeon, and the pigeon went from King's Landing to Westeros. No, that's still the same place. Anyway, right. He went from a castle to another, right? And he wrote the message. But this pigeon took some time to get there. Maybe he stopped for a little bite, or to found a cute little pigeoness and had a romantic thing. So, suppose he arrives probably an hour later. Well, if the message saying the king is dying, then perhaps by the time you read the king is dying, the king's already dead. That's the same thing with light.
That's quite a good analogy. I like that. Science and maths work together for this map work, and these are our perceptions. Could finding what is beyond our knowledge now about black holes, could that make time travel achievable?
Hang on, I've left you. I missed you. Some say you said sorry.
Let me put it on the screen.
Yeah.
It's a bit,
I'm looking for it too, but I don't see it.
I've put it on the actual screen if you can see the screen.
Oh, okay. Hang on.
Sorry.
So science and math work together. This map work. there are our perception. Could finding what is beyond our knowledge now about black hole, could time travel be achievable? Yes, time travel. That both to find the thing with time travel is that it is not impossible mathematically, and that is because time is one of the dimensions. So if you move through space-time, you can move through space, but you can move through time. So from as far as the maths is concerned, time and space are connected in the same continuum. Now, it is in a way possible, like if you're talking about black holes. Yes, black holes where time actually, I mean, what happens to time in that warp? The time, because it's a point of singularity, time becomes zero. So if you look at those equations, and the energy becomes infinite. So what does zero time mean? It means that all times happen at once. So could falling in a black hole put you in a space where there is no time and all times are at the same time? This has been used a lot in science fiction movies and in the good science fiction movies. And we have no idea because, yes, we just took the first pictures of a black hole. Wow, that was in only 2 years ago, it's 2021. And it's a great achievement, but yet we cannot see really what happens really inside it because it's all black. So we took the picture of it outside, right? Before we couldn't even see that. Now we can see what it looks like, but we can see only at the edge because light disappears inside and we can't see nothing. And so if you cannot see it, you cannot study it. This is why if we can create black holes in the LHC, these micro black holes that live for a split second, then we could have something in your lab that you can study, because you can't go and study up there in the universe. And that could probably tell us an answer to your question.
Talking about things we possibly have no idea on. How did we get here?
How did we get here? You mean to this level of knowledge of mankind?
I think he means the existence of mankind, potentially.
Yeah, well, in that case, yeah, the existence of mankind. Well, that was the question was mostly about the antimatter and the fact that we should have annihilated completely all matter, us, the stars, the clouds, the water, everything should have annihilated into a flash of energy right at the beginning of the universe. And we cannot understand why we're here, though we have our first clues, because for the last 20 years or so, we've been finding some particles that interfere with this law that says you've got to have one boy and one girl and you cannot have only one. So you have to have, every time you disintegrate and recreate, that recreation must be always a negative and a positive. However, there are some particles that could elude this symmetry and end up decaying into only one, possibly matter or antimatter. But eventually, it looks like it's more likely to be matter because we are here and we exist. The other question.
We've lost you for a couple of seconds, potentially. Give him a couple of seconds to see if he comes back, guys. Okay, I'll give it a couple more seconds. If he doesn't, then
Okay, I'm back.
You're back. Good. Cool.
Sorry, yeah, there are always. I funny just over an hour. There's always it's 1 hour 20 that we've been connected, 1.5 hours, and there's always this kind of breaks every now and then. But okay, I'm always back. So yeah, so my question was, how are we still alive? Not how we're here, but how are we still here and not disintegrated against some black hole or a supernova or asteroid that falls on us? The universe is such a scary place, actually.
Okay. So you could actually study micro-manufactured black holes at CERN? ? And there was an ad on it, and it would be safe enough.
Well, yeah, like I said, like we study protons, I mean, like we study muons and kaons and pions and all these intermediate particles that are very short-lived, live only a few, less than a picosecond, 10 to the minus 24, 10 to the minus 16, so they live for such a short time because they're unstable. And what happens is that you create them from a collision, and then they will decay into something stable, like protons, neutrons, etc. So if these black holes, if it's possible that these black holes are manufactured, we're probably already manufacturing them, except that we can't see them because our detectors are not refined enough. That means when you hit two protons, all the possible particles that could be created are created, in that flash of energy, except that we can only track those that we have the technology to track. That means they live long enough and they interact with our sensors. We have detectors that are layers of electronics that can track only one kind of particle. So there is the layers for the electrons, the layers that track the muons, the layer that tracks the kaons, the pions, the quark, etc. So in order to see these things, that we have to have. One problem with black hole is that we don't know if they have a charge. Would they have a charge? Non-charged particles are very difficult to track because they don't induce currents in electronics. We have silicon detectors, etc., that when a particle passes through, it generates a current in there. So the computer will know, we've seen a current, and this is the amount. So it can, by the amount and then by the direction, we can say what kind of particle that was. But black holes, we have no idea. Do they have a signature? Do they have a charge, an electric signature? Don't know. However, we can find what is called the signature of particle, and that is, for instance, the Higgs boson. The Higgs boson does not have a plus or a minus or anything. But the Higgs boson, we know by theory that it would decay into like two muons and two electrons, I think. Correct me if I'm maybe photons. Anyway, it would decay into a particular structure of particles. So if you see those particles, means that there must have been a Higgs boson there. So probably with a black hole, we can see something like that. The black hole would disintegrate so fast. That's why we don't see them, that we can't even register it. But we could register some perturbation to space-time that he could have done, always in a microscopic level. So this is why, it's safe, because it's not any more dangerous than imagine a battery, imagine a 1.5 volt battery. Now take this battery and make it so small that you need a microscope to see. How dangerous would that be to you? Would it electrocute you? This doesn't electrocute you already. So how would that electrocute you? It's the same. That's the analogy I can think of to make you feel safe.
Yeah. When you had the map up at the start and you had the different areas, you said you had like Atlas and Alice and something else. Do you say they were different experiments or?
Yes. Well, what are they? They are, see, the Large Hadron Collider accelerates protons and collides them 40 million times a second in 4 points. These 4 points, we built these gigantic cameras. I call them cameras. They're not really cameras like this one. No. They are not that. They are detectors. That means they are like onions of electronics. And all these layers, one inside another, are able to track the passage of particles, because each layer, when a particle crosses a detector, imagine all these these sheets here of paper are different layers of electronics. A particle passes through, will pass this layer, the layer. They pass them one by one, and each one will come back and say, hey, I've seen one, I've seen it, I've seen it. And so you can know where it's passed. You can trace the direction. So that's how a detector works. However, you can use a detector to look for several different kinds of particles. So for instance, LHCb is looking for antimatter, and they are trying to study what you call the CP symmetry or the CP violation, as I said last time we spoke about antimatter. Why antimatter and matter are not quite the same. So then there are CMS, the one on top, compact muon solenoid, and Atlas, which is the one at the bottom. That both are the ones who found the Higgs particle. They're all looking for large things, for something big. Now, the next thing they hope to see is something like dark matter, any signature for dark matter, that could form in this micro collision. Then the other one, Alice, is studying the primordial soup. That is, back at the time of the Big Bang, when the first particles started forming, there were all quarks and gluons, which are forces that connect together the quarks. A proton is made of quarks. There are quark, one up and two down, so two down and one up, and they form proton, neutron, antiproton. So these quarks are glued together, by something called the strong nuclear force. Now, this force is like a glue, and that's why they're called gluons, the particles that connect the quarks together to make a proton or a neutron. Now, they're studying the universe. So in that moment, before the actual protons and nucleus form, there were these quarks and gluons floating about in the universe in an unconfined, which means in a free state, like unleashed dogs. And no, they're trying to take a picture of that to understand how the universe was back then. See, understanding your origins always makes you understand today, the reality. So that's why they're looking back in the past.
Mm. So the LHC and the CMS are just the anagrams of. So what does that make Atlas and Alice?
Atlas is a toroid solenoid. I don't remember the exact anagram, but it's a toroidal solenoid. So it's a bit like CMS, but it's got a toroid form, like an octagon, like that, made with large magnets, huge magnets that are disposed in a toroid shape. If you look it up, Atlas, look at the pictures, and they will show you all the detector of Atlas CERN, of course, because there's many atlases around the world. Businesses called Atlas. So look for Atlas CERN, and you will see or Atlas detector, and then you will see the structure of the Atlas, as well as the CMS detector. You'll see all the structures there. They're very interesting. They're very amazing stuff to watch when you're there. You feel so small. These things are like, they're like 26 meters tall and 60 meters wide, dense with electronics, and it's all these layers that move around and close because they have to open them to maintain them. So, but when it's open, it's wow, it's something that makes you really mind-blowing. And I had the chance to see it, of course, because I was going there with a camera to film as I was making the films for CERN back during the construction of the LHC. But people are still able to visit, except I can't promise you may be able to allowed to go down in the pits. The problem is that they stopped the Large Hadron Collider for a very short time to do maintenance, and they cannot have visitors at the same time. They only, there's only VIPs are let down there, or physicists, people who go there for a reason. It's very unlikely that they get tourists, unless it's an open day. Sometimes they do open days where they organize systematic visiting of the detectors. And if you happen to be, or if you can go to Geneva to CERN there, you just get in touch with the visit service and ask if you could be allowed. You have to book, of course, because there's a problem there, is that you can't not let too many people. You have to. There's a limit. I can't remember if it's 12 or 15. You cannot be more than that in the pit, even though it's a huge pit. But you can't, because it's probably 30. I can't remember. Anyway, it has to be something that the lift can carry upstairs. Because if there is anything, it can be a helium leak. There could be, anything, any fire, short circuit fire. Nothing ever happened like that. But they, security, so they have to make sure you're safe. And therefore, they have to let stay there, only the amount of people that can make it back with a lift, in one go. Okay, sorry for the digression, but it's interesting to go and
Yeah.
way.
So they're all basically just anagrams of what they're looking
CERN's
for.
got like about 40 experiments. The ones on the LHC are only some of them. Last time, when I spoke about antimatter, I showed you the AD, the antimatter decelerator, which is a totally different accelerator. There are like 10, 12 accelerators at CERN, one connected to another or not connected. This one, the AD, was producing antimatter in the bottle and keeping it there in a magnetic field in suspension to be able to study it. So it was there, so you can actually see these atoms of anti-hydrogen that they are building. It's called the antimatter factory, because we build anti-hydrogen not to sell it or to make a bomb to explode the Vatican, like Dan Brown wants us to do, but to study it, to understand how it works and how is it different from normal matter.
Okay. I think I've probably missed a few, but I'm sure I've noticed on the last couple of shows you've gone through afterwards and answered anybody if I've missed them.
Because now we're hitting 1.5 hours, so I guess we should call it. But I will go through them tomorrow and I will reply. If you still want to ask questions, you're free to do it on the comments and I will reply anyway offline. Yeah,
I think I've got most people's, but because I was asking the last couple, I lost a few going up. So like I say, I'm sure you'll get to them anyway. And thank you very much for your time again. And we will be back next week, guys. There's not a show tonight now. And the next one will be tomorrow morning, will be Digillution at 11 a.m. British Summer Time, which equates to 8 p.m. Australian Eastern Standard Time. And we will see you all soon. Good night.
Goodbye.